both of your graphs in front of you. Okay, so you should now have two graphs, one from last lesson, one from this lesson. This is the one that we've already talked a little bit about, but we're going to talk more about it in a second. And this is kind of the graph that you should have just arrived at from today's lesson. If you didn't, can you just scribble on the chat or unmute and let me know now if it's all gone horribly wrong? Okay, so we are going to ask about these graphs, but just before we do, I said last lesson that we were opting to use a voltmeter because I have lots of them lying around. They're easy to use. You're comfortable with them. You know what they do. But that we could have measured the other variables that are in play, like the current in the circuit and the charge on the capacitor. So rather than actually measure them, we're just going to use the equations we know to convert the PD values into charge values. So my first question is, can you think up an equation, maybe from 2 lessons ago when we started this topic, that relates the potential difference to the charge, which would allow us to convert the potential difference values for both graphs into charge values for both graphs? So maybe unmute and call out an equation or scribble it on the chat, up to you. Do you have an equation?
Q equals VC.
Very good. So in which case, the charge values are just a multiple of the potential difference values. So on a different piece of paper, not your graph paper, just in your notes somewhere, could you sketch, like I have sketched on the board, you don't need the numbers, could you sketch for me these two graphs, V against time, and then underneath both of them, could you sketch me a Q against time graph, and then leave yourself enough space, because underneath that, I'm going to be asking you to sketch me what you think the shape of an I against T graph would be. So you're going to have 6 graphs down your page, 3 on the left, 3 on the right, for charging and discharging. So I'll just give you, what, 2 minutes to very, very quickly sketch yourself some axes, sketch those 2 graphs, and then underneath it, sketch what you think a charge graph would look like. Don't worry about the numbers up the side of the graph unless you want to. Okay. Anybody want to describe the shape of the graphs that they just drew for the charge? You're feeling shy this morning?
I just drew the same exponential decay graphs as I did for voltage.
Very good. Potential difference, not voltage, and that's not an exponential decay graph. So what did you draw up for the charging one? The same?
Yep.
Yeah, okay. So yeah, you can just change the axes. Bearing in mind you haven't put numbers on yours, I have, but you can just relabel this charge in coulombs for both graphs because the charge is just a multiple of the potential difference. I'm going to put that back because I have got numbers on mine. Okay, we now need to think about the current. So same question, do you know any equations that happen to have potential difference in it and also current in it so that we can switch from one to the other? So anybody want to shout out an equation?
V equals IR.
Very good. And again, just like Q equals CV, I is just V times some number, in this case 1 over R. So again, it's just a multiple of the potential difference. So what I will ask you to do is same thing. Could you complete the two graphs underneath? However, this graph's okay. And if you are not seriously very careful, you will mess this one up. So that one's straightforward. Go for it. But think long and hard before you do that one. I'm going to give you another 2 minutes, and then I'll ask you what you drew.
I don't think we can hear you, sir.
Thank you very much. I'll say all that again, shall I? Unless you can liberate. Okay, so for the current graph, you should have drawn exactly the same thing, because as you just told me, I is just V over R, it's a multiple. And that's because we've got a capacitor, a potential difference V, and that's driving the current I through a resistor R. However, talk me through the mistake that you might make for the second graph. Did you draw that for the current? Any ideas? Do you think the current starts small and finishes big? Can you see in this circuit compared to this one? There are two EMFs effectively. This one's trying to drive the current anti-clockwise around this circuit, but as this capacitor charges up, this plate will match the positive plate here, and this plate will match the negative plate here. This potential difference is going to oppose this one. And by Kirchhoff's second law, we need to subtract off, or add, but this one's negative, the PDs in a closed loop. So when we apply this formula, this V here is the total EMF in the circuit, or the total PD in the circuit, which means we actually need to write V0 minus V equals IR. And now when we rearrange it to get I, we get V0 over R minus V over R. Now V0 over R, that's the full 6 volts divided by the resistance. So that's what we will get as our current when there is no V on the capacitor. So this bit here, this is I0. That's the initial current at the beginning. And then after that, we are subtracting off this graph divided by R. So at the beginning, we subtract off basically nothing. But at the end, we subtract off a lot. So do you want to make a prediction of the shape of your graph when we take a constant value and subtract this value off it? What kind of shape do you think we will end up with there?
Will it be like the graph on the left?
Yeah, we'll be able to like the graph on the left. So the current for the charging graph, it bucks the trend. It's not going to be this shape like the potential difference in the charges. It's going to be just like this one. It's going to start with a large current, I0, and the current will start big because there is a big potential difference pushing it from the power pack and very little to oppose it. But then as the capacitor charges up, we would expect the current to get smaller and smaller and smaller and smaller and smaller because it is so much harder to add every next electron onto the capacitor because it is already so charged. Okay, if you haven't quite got those notes back, I'll post the video in a second and you can copy them down. I think we're kind of running out of time. The thing that I would ask you to do before next lesson is somebody use the word exponential decay today. Bear in mind when you add the word decay to that, it means getting smaller. You would rather describe this one as exponential growth. We've mentioned exponential ever so slightly in the past. If you don't remember mathematically what the word exponential means, it's got a very defined mathematical meaning. And if you don't remember how to show it from a graph, simply by pointing at values on this graph, you can go, hey, look, it's an exponential graph because. Could you please look into that for next lesson? Could you please just make sure that you have an understanding of why we can use the word exponential with regard to this graph, and what data would you pluck from the graph to prove it. Okay, I'm going to leave it there. Next lesson, I think it's Friday, isn't it? We're going to start asking if we can model capacitance based on the physics we know to actually predict these graphs as an outcome. And we've done this many times before. Remember, I'm kind of teaching you the mathematical modeling side of the A-level course. So we've now got some data. We've got a physical understanding of what's going on. We should now be able to take a mathematical approach to mathematically model what's going on using the laws of physics that we know, that will result in predictions of these 6 graphs for the charging and discharging capacitors. Okay, get yourself all caught up and make sure you understand it for next lesson. Have a look at the word exponential, pull some data off this graph to demonstrate it to me, and we'll pick this back up on Friday. Thank you very much. Off you go.